Hi, my name is Riley Frost and I'm an undergraduate student at the University of New England. Today I will be explaining and demonstrating the background behind and use of a gas chromatography mass spectroscopy instrument. Gas chromatography mass spectroscopy, otherwise known as GCMS, is an analytical technique that couples the features of gas chromatography with that of mass spectrometry to identify different constituents within a sample mixture. Gas chromatography was first widely noticed in 1951 to 1952 by Anthony T. James and Archer J. P. Martin, who earned the 1952 Nobel Prize in Chemistry for their gas chromatography research and discoveries. Gas chromatography and mass spectroscopy paired up around 1950 through the research of Fred McLafferty and Roland Golk. However, a GCMS instrument was not officially produced until 1955 to 1956. Gas chromatography and mass spectroscopy are two different analytic methods on their own. Alone, mass spectrometry identifies chemical substances by sorting the gaseous ions of the different compounds of the sample in electric and magnetic fields on a spectrum that compares the mass-to-charge ratio and percent abundance of a substance. Gas chromatography separates and analyzes compounds of a sample that can be vaporized without destroying the compound. Gas chromatography can be used to test the purity of a substance, help identify the substance, or separate the compounds of a mixture. How GCMS works. GCMS occurs through a series of four main steps. The first step is sample preparation. In this step, a sample is dissolved or diluted in an organic solvent and is injected into the inlet port of the GCMS instrument. However, some samples are further prepared through solid phase extraction or derivatization. In the next clip, I will demonstrate sample preparation. As you can see in this demonstration, I pick up my GC vial and use the capillary action of a glass pipette to drop a few drops of sample into the vial. Only a few drops of the sample are needed because the GCMS instrument is very sensitive and any more could damage it. After doing so, I filled the rest of the vial 2/3 of the way full with the organic solvent acetone. Once done, I relatively tightly cap the vial and I make sure that it and all of my other vials are labeled with the time point that they were taken and are ordered correctly. Once you have taken all of your samples and you are ready to insert your vials into the GCMS machine for analysis, it is very important that you rack them as I demonstrate. You start in the top right of the rack, and then you work down the row, and then continue at the top of the next row. Once your vials have been correctly put into the rack, they are ready to be inserted into the instrument. On your rack, there is a number corresponding to its position in the instrument. Place accordingly. Now that your samples are in the GCMS instrument, the instrument does the rest of the work. Based on your model of the GCMS instrument, you should choose the correct settings for the best analysis of your samples. The remaining 3 steps of the GCMS process are done by the instrument. The next step is called vaporization. In vaporization, the liquid sample is heated and vaporized into a gas after entering the inlet. After being vaporized, the mobile phase occurs, which is step 3. In the mobile phase, an inert gas is responsible for carrying the gas state sample through the gas column. In the gas column, a chemical entity is present that allows for chromatography to occur. This is known as the stationary phase. The stationary phase of the column interacts with different molecules completely differently, and therefore the substituents of the molecule will be separated as their travel rate through the column will differ. Now that vaporization and the mobile phase are complete, the gas chromatogram portion of GCMS is done. The last step is the detection of the sample by the mass spectrometry instrument. In this step, as the different compounds of the original sample pass through the column, the mass spectrometer will break the compounds into ionized fragments. This is done as a high-energy beam of electrons passes through each individual fragment, creating a cation. These fragments then travel through a short tunnel while being exposed to a magnetic field in short periods of acceleration and deflection. At the end of the tunnel, all positively charged fragments will be detected by a detection plate, where their mass-to-charge ratio and relative abundance will be measured and graphed. Now that the instrument has finished processing your sample, a chromatogram and a graph will be produced for your sample. The last 3 steps that I described will need to be carried out for all of your samples, and one sample usually takes about 10 minutes. However, once the process is complete, you will have data similar to what is shown on screen. You can further analyze the data that has been produced to aid you in your experimentation. Thank you for watching my short video about GCMS. I would like to thank the University of New England's School of Mathematics and Physical Sciences for the facilities and materials provided to allow me to make this video, and my professor Amy DeVue for guiding me through this project.